Hi there, I'm Daryl Percy. I'm an electrical engineering student at UBC here in Vancouver, and I want to be talking today about distributed control systems. And in particular, I'm going to be talking about how they're applied in heavy industries like mining and oil and gas, and what are those applications and how are they tuned. So let's get.
First, I'm going to give a preview of what we're going to be talking about today. I'm going to try to motivate why you'd want to bother with control, especially we're talking about in industries like oil and gas, mining, and pharmaceutical, heavy industries here. Then we're going to talk about what distributed control systems are. These are the big multi-million-dollar enterprise class systems that big companies are putting in their plants to control every aspect of their operations. We're going to talk about what the parts of them are and how they interact. Then we're going to talk about how the control is tuned, because even when you spend a lot of money on your DCS, it still doesn't necessarily work right out of the box. Every little part of it needs to be optimized. We're going to talk about the importance of modeling the plant in order to achieve that tuning. Then we're going to talk about how the modeling is done through bump testing, which is a little bit different approach than what's been taught at UBC and the control courses that are available to us. Then we're going to talk about real PID tuning and how it's done in the field, which again, even if you know about something like, for example, lambda tuning or pole placement, these type of theoretical techniques that are taught, it's quite a bit different than what's done in the field, so I'm going to go into that. Then we're going to talk about just a little bit of theoretical detail about how it works, how the modeling works, how the tuning works, and why it's done the way it is. Okay, and let's.
So why do you bother with control if you're working in heavy industry? Well, why don't we just take a look at an example? Let's say you're working at this nice Shell refinery.
So we're going to take a look at this pipe here, and in particular this tank. And Shell is a profit-making corporation, and the margins sometimes, especially in a place like Alberta and the oil sands, the margins on oil are not good. If the price goes down, it's no longer economically feasible for them to operate their oil operations there. So in this case, you want to optimize everything you're doing to make it as profitable as possible. So here's a cutaway drawing of the tank that I did, and we're going to take a look at the parts here. In particular, we're going to focus on the valve, and we want to control that valve. It's important that we control the level of the tank. We don't know really why we need to control it, why it needs to be here, but the chemical engineer or the process engineer who designed this for Shell Corporation says it needs to be here, so that's our job to make sure it stays there. And we're going to do it by manipulating this valve.
Here's an example of a valve you might find in one of these operations. You've got the actual valve part here. This is a pneumatic actuator. The air pressure comes in through this line and down through the top. It presses down on a spring and operates this rod, and that can open and close the valve. And then here you see some instruments. Got some probably air pressure measurements here. This particular valve happens to be kind of a fancy one because it has its own little controller here that can be doing PID control on this actuator. But in most cases there isn't going to be a little controller here. There's just going to be the instruments. So the question is, how are you in general going to control a valve? Well, the first thing that comes to mind is you might want to control it by hand. And here's an example you might be familiar with from the well-known Dorff and Bishop control textbook. You see the control technician controlling the level of the tank just like we are by manually turning this crank. And this is something that really is done. Here's an example. So you've got the wheel here. This is for when your control breaks down, automated control is not working, or when you just need to make safety adjustments, or you just need to go into manual mode to do testing. And that's something we're going to look at later, that manual mode really is used. It's not just something that is neglected. It's used for testing. But ultimately we want to get automated control. So to make our automated control happen, we're going to install a tank level sensor. Here's an example of one. This one happens to be radar based. You'd probably install this here at the top of the tank, and it would shoot radar beams down to find the level. This here is a gauge, and it would be transmitting the signal. So where does the signal go? The signal goes to this little controller that happens to be located right on the valve, and that controls the actuator and controls the valve. Now, as you can see, you might be familiar with this diagram from your entry-level control text. That sensor and that valve form a closed loop. This is the so-called closed loop control. The sensor is here, sensing the tank level, the so-called process variable. It goes here, it gets compared with a reference level, or a set point as it's called, and the error gets fed into the little field controller that was on the side of the valve, and the valve controls the process, which is here represented by the transfer function, and that is your closed loop. The same idea of closed loop control can be applied to controlling the temperature. You know, in these big petrochemical plants, you can have certain tanks at 1,000 degrees Celsius plus or minus a few degrees, and then a few meters away from that you can have another tank at negative 100 degrees. There are really extreme temperature variations in these plants, and you got good temperature control is very important. Otherwise, you could lose an entire batch and damage your equipment. Pressure control, you could have, this could be pressure in a air conditioning system, or pressure in a valve, pressure in a tank. You've got flow control, that's rate of flow. There's so many different things that can be controlled, and you want to do this to make as much profit as possible. Well, what is distributed control? You know, in a facility like this, you don't just have one valve, you have thousands of valves, you have thousands of pumps, you have thousands of motors that need to be tuned, that need to be operating at the right time and having a good response when things change. So here are some real examples. You've got the Rio Tinto Diavik diamond mine. This is up in Nunavut. You've got 5,000 I/O in this plant. So I/O is kind of the control engineer's term, talking about how many input and output signals you're dealing with. And in this, so you could have, those could be valves, those could be temperature sensors, pH sensors, they could be many things. But they've got 5,000 of them, so they've got to manage all of those. Here's an even bigger one. You've got this refinery in China. This is the biggest one I could find. I'm sure there are even bigger ones. Distributed control systems, the big enterprise class ones, can handle up to 1 million I/O. So you might think that you want to have a central control room with a big central control computer controlling everything from one location, but that's typically not how it's done. You know, there are some problems with that. What if your supercomputer requires maintenance, and you don't want to have all the wiring coming into one central location? It becomes really like impractical. So here's an example of a real distributed control system. This is how it's done in large plants. This one happens to be from Emerson, their famous Delta V system, and we're going to go through all the different parts of it. So these are the field actuators. There are thousands of these through your plant. We're talking about pumps and motors. We're talking about valves. These are the things that need to be controlled. Then you've got sensors and transmitters. These can be like temperature sensors. This one is a Coriolis sensor. It measures flow. This one is probably a pressure sensor. These here might be like pH sensors, temperature sensors. And now where's the information from these sensors going? It's going into these PLCs, Programmable Logic Controllers. But it needs to be first received. So you've got these I/O receivers here that are receiving the signals. The signals can be analog or digital. That's quite important. We'll go into all these details. The PLC does the logic to do the control, and it sends the control instructions back to the actuators to actually do the control. And finally, we've got the highest level here, which most people think of when they think of distributed control systems. You've got the high-level control center monitoring, the data analysis, the data collection, and we're going to go into what. So we're going to talk first about the actual actuators in the field. Actuators that just refers to the real motors that are doing your work in the field. We're talking about the pumps and the valves. We've already seen an example of a valve. And we also here you've got this one here. Looks like it's probably either a valve, and this one is probably a pump. So there's thousands of these all over your plant. They can be located really far from the main control room. We're talking about kilometers in some cases. And as we already saw an example where a valve might have its own little controller on it, so it doesn't need to be controlled by a PLC. Then you've got your sensors and your transmitters. We've got temperature sensors, thermometers. This one, as I said, is a Coriolis sensor. It senses flow, rate of flow. This one is probably a pressure gauge, pH, all kinds of different sensors and transmitters. They have both digital and analog signals. It depends on what you're sensing. There are proprietary and open standard communication buses. So some of them, DeviceNet is a very popular one that I believe is open source. Then you've got ones like Profibus that are closed source. That one's by Siemens. So, and they all need to be able to talk to each other, because you can have your equipment from many different vendors. You don't just have your equipment from one vendor, although vendors want to lock you in, but they all need to be able to speak to each other. That's very important. Wiring is a huge problem with sensors. You need to hook up your sensors to something. You need to get the information from your sensor to the computer, and wiring is a big cost, and it needs to, obviously somebody needs to wire it up, but it also takes up space. It's prone to getting cut. There's many problems with it. Adding new sensors to your plant, like if you decide you need better data about a process, it may not be easy. Not only do you have to shut down the process in many cases, but it may be difficult to wire it. It's just expensive to do. Wireless technology helps with that a little bit, but in many cases companies don't want to just rely on wireless all the time. Next, we're going to talk about the PLCs that do the actual control and do the actual logic. You might wonder, what is a PLC? Well, basically they're using commercial off-the-shelf parts. It didn't used to be the case. Up until about the 90s, they were using their own custom chips and custom hardware, but that no longer was economically viable, and so the companies that are using custom off-the-shelf parts are the ones that dominate the market now. They're not really that different internally from a PC. They use standard parts that you might have in your own PC, like Intel chips. But the difference is that they're designed for the rugged conditions like vibration, humidity, temperature that you're going to find in these plants. And they have custom operating systems that are highly reliable. So here's a modern example of a PLC. This is a recent model Delta V system from Emerson. You'll notice it's mounted in a rack, and the racks are mounted throughout your plant. Typically the racks are mounted pretty close to your process, close to your pumps, close to your valves. That saves wiring, and your technicians can move throughout the plant and make changes and modify this system as they see fit. The racks are modular. You've noticed here, like, there's all these little components. These can be taken out or put back in. You can change your arrangement as you need it, put in new components as your process changes. These are I/O units in here. They can accept both analog and digital signals from different protocols. I mentioned DeviceNet. Here you see some mentioned up here, H1 field bus. I think that one's proprietary to Emerson. You need both analog and digital signals. So an example of a digital signal would be like the big red emergency stop button that will be throughout your plant that are required by safety regulations. But then also, if you're measuring things like temperature, well, that's going to give you analog data at some point along the line. So PID control also requires analog data. It's basically an analog method, and so you're going to need to convert that analog signal to digital in order for it to be processed by the PLC here. So these I/O units tend to do very good analog to digital conversion, and they can take many different types of signals. So I'm going to talk a little bit about the types of signals that you're going to see in the plant, and typically the 4 to 20 milliamp analog signal is preferred in industry in North America to the 0 to 10 volt DC signal, although both are used. Some of the reasons why the current signal is preferred is because if you're establishing a voltage, if you have, say, a temperature sensor that's transmitting a 0 to 10 volt analog signal, and where 0 represents the low measurement and 10 represents the highest possible measurement, well, there's going to be some voltage drop across the cable between the sensor and when it reaches the I/O unit here. So the I/O unit is not going to see the real accurate measurement that's being sent by the transmitter. So you need to take into account voltage drop. Nobody wants to do that. There can be noise from other devices on the line. Now, that's a problem for voltage. Now, at first, when I saw that, I thought, if the line has such and such an impedance, then if there's noise in the voltage, shouldn't there also be noise in the current? But then, really that's not the case, because the 4 to 20 milliamp signal that's used, that essentially the transmitter that's putting out the 4 to 20 milliamp signal, that's like a constant current source, and there may be a small amount of noise on the line, but basically the current that leaves the transmitter also arrives here at the I/O unit, and noise doesn't really affect this constant current source, whereas with the voltage source, especially on a very small time scale, like on the millisecond or microsecond time scale, you can get pretty bad noise in the voltage measurement, which can obviously affect your control pretty badly. Another reason why you might prefer the current is because it's easy to detect connection problems. If, for example, if you have a short circuit in your voltage signal, you'll be seeing 0 volts here at the I/O unit, but the thing is, you can't really distinguish that easily between the 0 volts that would be just a standard low measurement or the 0 volts from a short circuit. Likewise, if you had an open circuit, the I/O unit here would be seeing some sort of floating voltage, maybe with a little bit of noise around 0 volts, whereas at this point your wire's been cut and it's just hanging in space, but you can't really tell because you're just seeing something that is not that unusual for you to see. So whereas with the 4 to 20 milliamp signal, if your line gets cut, and you're seeing zero amps, then you know that there's a cut in your line. So these are reasons why the current is preferred. We're just going to talk briefly about wireless I/O. One of the big advantages of wireless is obviously it saves wiring. This is an example of a modern Delta V wireless I/O unit. You can see these modular I/O cards that are receiving wireless from different signals in the plant, and they're going into this PLC. Frequently, companies don't want to rely on wireless for all the reasons that you've probably experienced with your own wireless routers. Well, they have the same concerns, and their processes, if they go down, it can be millions of dollars per hour that they're losing. So, yeah, obviously they don't want to rely on that. They have wiring for reliability and then wireless also. The PLCs are programmed in this ladder logic language. You might notice some of these symbols. These are relays, and here's a coil. This probably represents a motor of some kind. So the technicians, when PLCs were first introduced, technicians were used to this sort of diagram already, because in the past control was implemented with relays like this, and technicians were wiring up their plant to implement their logic in hardware. So they were able to more easily adapt to the PLC with this type of language, and it's still widely in use today, although there are other languages as well using function blocks and whatnot. So now we're going to talk about the top level of DCS control. This is the data analysis and monitoring level. You'd find these computers in the central control room. That doesn't mean that these are the brain, so to speak, of the control system, because as we've already seen, the logic and the control is really located on the shop floor in the PLCs. What does this do? Well, it collects the data history, and it allows you to do remote programming of the PLCs so that technicians don't have to go out into the plant and plug into the PLC with a USB cable or something. It can be done from the central control room. As you can see on the screens here, there's a vision of the whole plant. If something goes wrong, the people in the control room can see it. You can switch to manual mode and adjust your actuators as you see fit. And also, something I'm really going to focus on here is that expensive DCS systems have algorithms built into them that are always improving. And these algorithms look at the historical data that they've been collecting, and they run tests on it and simulations with it to try and obtain an estimated model of your plant. And this is very important. So how does the DCS use all this data to build your plant model, and why do you care about that? Well, what's the importance of modeling your plant? If you've done any courses in control, then you've probably seen some methods for PID tuning or general control tuning, where you're trying to get certain behavior out of your controller. You're trying to get your behavior to respond a certain way. And here you've got examples: internal model control, pole placement, lambda tuning, Q design. There's many others. These are all Laplace domain techniques for PID control or general controller design to get it to do what you want. But one common feature of these is that to use them, you have to have a model of your process. So at UBC Electrical Engineering, and I'm sure a lot of other universities around the world, modeling is taught like this, where you're told to obtain equations from first principles of physics capturing the dynamics of your system, and then go into the Laplace domain and come up with a model of your plant. Using first principles of physics is all fine and good as long as you have a well-understood system and a well-behaved system. Like this one, for example. I'm sure everybody watching this right now has at some point derived the transfer function from V in to V out for this nice inverting op-amp. It's no problem. And in fact, these same techniques are used on a larger scale in analog IC design or digital IC design, integrated circuits, mechatronics, even in aerospace. In the case of an aerospace company like Lockheed or Boeing, they would have PhD physicists on site who would have a sophisticated understanding of the dynamics of the air that's passing over the wings, and they would be able to come up with differential equations that really do describe those processes. Using first principles of physics is all fine and good as long as you have a well-understood system and a well-behaved system. Like this one, for example. I'm sure everybody watching this right now has at some point derived the transfer function from V in to V out for this nice inverting op-amp. It's no problem. And in fact, these same techniques are used on a larger scale in analog IC design or digital IC design, integrated circuits, mechatronics, even in aerospace. In the case of an aerospace company like Lockheed or Boeing, they would have PhD physicists on site who would have a sophisticated understanding of the dynamics of the air that's passing over the wings, and they would be able to come up with differential equations that really do describe those processes. Using first principles of physics is all fine and good as long as you have a well understood system and a well behaved system. Like this one, for example. I'm sure everybody watching this right now has at some point derived the transfer function from V in to V out for this nice inverting op amp. It's no problem. And in fact, these same techniques are used on a larger scale in analog IC design or digital IC design, integrated circuits, mechatronics, even in aerospace. In the case of an aerospace company like Lockheed or Boeing, they would have PhD physicists on site who would have a sophisticated understanding of the dynamics of the air that's passing over the wings, and they would be able to come up with differential equations that really do describe those processes. Using first principles of physics is all fine and good as long as you have a well understood system and a well behaved system. Like this one, for example. I'm sure everybody watching this right now has at some point derived the transfer function from V in to V out for this nice inverting op amp. It's no problem. And in fact, these same techniques are used on a larger scale in analog IC design or digital IC design, integrated circuits, mechatronics, even in aerospace. In the case of an aerospace company like Lockheed or Boeing, they would have PhD physicists on site who would have a sophisticated understanding of the dynamics of the air that's passing over the wings, and they would be able to come up with differential equations that really do describe those processes. Using first principles of physics is all fine and good as long as you have a well understood system and a well behaved system. Like this one, for example. I'm sure everybody watching this right now has at some point derived the transfer function from V in to V out for this nice inverting op amp. It's no problem. And in fact, these same techniques are used on a larger scale in analog IC design or digital IC design, integrated circuits, mechatronics, even in aerospace. In the case of an aerospace company like Lockheed or Boeing, they would have PhD physicists on site who would have a sophisticated understanding of the dynamics of the air that's passing over the wings, and they would be able to come up with differential equations that really do describe those processes. So this presentation is about heavy industry like oil and gas and mining. And I was kind of skeptical when I first learned these techniques like Laplace domain optimization and modeling, that a place like a refinery or a mine would have people on staff that were qualified or willing to write down differential equations describing the dynamics of all the fluids flowing through all these pipes and going into these tanks and having their state changed by thousands of degrees. I mean, look at this thing. It's huge and quite intimidating. And this is just a small, this isn't even that big of a plant. I mean, this is just a small snapshot of a plant. Imagine one with 35,000 I/O like that one we saw before. I just didn't believe that industry would be spending time modeling that with differential equations. So I looked into that, and it turns out that industry does use other techniques. They're not modeling it with differential equations. So I want to get into how that's done. So these are some people that I either talked to or read their thoughts about this topic. This gentleman I spoke to, he's a master's of control, and he works for a major automation vendor that does a lot of work in big industrial plants, and he actually thought it was quite funny that I was even suggesting that you would use Laplace domain techniques or differential equations, because he said you just don't have a model of the plant. That's just how it is in his line of work. Here's another gentleman, this engineer Mike Brown. He travels the world educating staff and technicians and engineers on how to better tune your processes, and we're talking about major companies like Halliburton or Exxon. You know, they're bringing him in to train their people, and he also expresses skepticism about the usefulness of transfer functions or the availability of them at all. Here's another gentleman, Will Wagner. He's a chemical engineer, a professional engineer and control process design consultant. He likewise doesn't think that there's much place for differential equations in real industrial process design. That pretty much says it all. Now, it's important to note that these engineers are not advocating blind methods where you're like just tuning knobs and trying to see what happens, like trial and error, or Ziegler-Nichols, which is an old method where you have to force your plant into oscillation. So like, for example, if you're controlling the temperature in a tank, and it needs to be like controlled within plus or minus 2 degrees, but you have to force it into oscillation, and it's oscillating by 20 degrees up and down. That's obviously going to be really damaging to your process. You definitely don't want to do that, but it's part of these old methods that are still frequently used. And these engineers also are not saying that the Laplace domain techniques are fake or they don't work. These engineers are well aware of the Laplace transform and its applications. They're very knowledgeable about it. The issue in big industry is that you need a proper model, and you don't have that necessarily. What these engineers do advocate is running tests on your plant to get an estimated model, and we're going to go into detail about how this is done. This is the approach that you're going to find not only technicians and control engineers are using it, but also the big enterprise class distributed control systems like the ones we already saw. Their algorithms are also using this approach. Okay, how is real modeling done in heavy industry? And it's done by what's called bump testing. Now, this is the classical test. This is an open loop test. And what do I mean by that? Well, look here. We saw before a closed loop system that had negative feedback. If you look here, there's no signal, there's no measurement being fed back into the controller, there's no negative feedback, there's no reference. You just have the controller, and you're controlling that directly. And what you're doing is you're going to put a step, some kind of bump here. In this case, we put a step on the controller output, and you're going to see how that affects the process. Well, the next step is you're going to record. You're going to record your controller output. Here is the step, and you're also going to record the process output. So it looks like this in this case. Now, once you've recorded this and you're analyzing it, the data that you've got can reveal 3 key facts about your process here. The first is the process gain. The second is your process dead time. And the third is your process time constant. We're going to go into detail about what these things are and how they're obtained. The dead time, the gain, and the time constant, these are all for the process, and they give you a nice estimated model. Well, once you have those measurements, there are well-known empirical formulas that have been come up with over time by various experts, and you can basically just plug that data into these formulas and come up with the sorts of values you need to tune your PID controller. So in open loop test, you're going to go into manual mode. Now, I was talking before about how manual mode isn't just a joke. You really do use it, and this is one of the important areas where you would use it, not only when your system breaks down, but here to actually do these sorts of tests. Even if you have a closed loop system, there might be a closed loop system here with some feedback going in here, but you're not going to want to use that feedback and that whole system right now to do your open loop test. You disconnect it, so you're just in open loop, and you're just controlling the controller, and you just put the step output on the controller and see what comes out here. There's no feedback. Now, right here we've shown a step output, but the bumps that you're putting on the controller output are not always going to be steps. The pulse is a popular one, and this is considered to be good because it's less destructive than an output to the step output to the process. A step, you're bringing the controller up and then leaving it there, and the process has to go up to that level and respond to it. And that gives you good data, but you might not want to do that to your process. The pulse just gives you like a little blip, and you get to see the response of the process, and from that you can extract the type of data that you want. Double pulse is even better, because double pulse, you've got one pulse up like this, and then another pulse goes down, and they kind of cancel each other out. So you see the response of the process going up, and you see the response of the process going down, and in the end, the process has been you've at least helped the process return more or less to its original equilibrium point, so it's far less destructive to the process. And also there are various complex patterns that have been arrived at through research or through experience, using different types of noise and so on that get put out here on the controller and seeing what happens in the process. And so when these are just, of course, a step is often used as well. That's not to say that step is not used. It is used. But these are some alternatives that are frequently used, and certainly distributed control systems that have complex algorithms are looking for, they either use actively or they look for aberrations in the data that look like these, and they look to analyze that to find out what's going on, how does the process respond. Another fact about the bumps, or another kind of important point, is that you don't want to have huge bumps here on the controller output. You don't want to go from 0 to 100 on your controller output, because that's very jarring to the plant. You don't want to damage the plant. You want to have just small bumps, you know, a few percent in difference in the output. Whatever your output happens to be, you bump it up by a few percent and see what the result is. And that tends to be a lot easier on the plant. Well, now we're going to look at an example of a real open loop test that's being done on an air compressor. This is courtesy of a company called BTC Instrumentation. They have hundreds of videos on YouTube showing real control applications from industry. You're going to be able to actually hear the air compressor responding to the step that they put on their controller output. And you can actually hear the instructor talking to his apprentice there about what they're going to do with this data. And it corresponds exactly to what we're going to be talking about in this presentation. Now, another reality of testing is that in real big plants, you might have to do a closed loop bump test, which is different. You can see that the feedback is hooked up here. This might come about because you simply aren't allowed by policy or due to safety. You're not allowed to disconnect the feedback here just so because you want to perform some open loop tests. They might say, no way, it's too risky here, it's too expensive, we can't afford to have the system go down like that. So you have to do the testing here while the system is still in automatic. This tends to be safer than open loop. It's safer for the people, it's safer for the process. It's not as damaging to the process because the feedback brings the process back to its equilibrium point. Also, you get a faster return to normal operations. You know, you're supposed to be typically in closed loop, and you stay in closed loop, so you don't need to hook that back up or account for any changes in the process or wait for it to cool down or anything like that. But now a problem here is that the controller is now, you know, you're putting the step here on the set point, on the reference, and then you're viewing the output here. But that means that you're not seeing just the response of the plant, you're seeing the response of the controller and the plant together. And what you want is the response of this guy. You want to extract. Distributed control systems use known controllers here, so you know what the response of this is, and it uses algorithms to isolate the response of the plant from in this data here, in this output. An important consideration when you're doing open or closed loop testing is that you want your test to be free from noise or disturbances. You want the pure response of the plant to your step input that you're putting either on the controller or here on the set point. You don't want this input disturbance. This could be like something shaking your plant, shaking your pipe. You don't want this output disturbance either. This could be something shaking. And here's some high frequency noise. You don't want any of these things interfering with your results. Then it comes down to analyzing the model. Now, powerful distributed control systems, they do this for you. They have powerful algorithms, and we're going to talk a little bit about how they're doing it. These are modern techniques. There's other commercial software out there. You don't have to have a gigantic plant with a big expensive Emerson system in it. Or you can do the analysis yourself, as those technicians were doing we saw in the video. And we're going to go into how that's done. So starting off with enterprise class distributed control systems, here you can see some major vendors here, and they store, here at the data analysis level, they're storing huge amounts of data, and the DCS will compare this data against seed models. You'll start out with an estimated model, and it will compare algorithmically. It'll compare what it's seeing in your from little just bumps that happen throughout the day in your operations. It will compare that against what would happen in simulations on their seed models, and based on that it will adjust and improve the model. The latest research in this area is model predictive control. This is the latest technology that you're going to be finding in these big expensive systems. Model predictive control is using dynamic linear models, so the models change, and this is based on test data, and it's able to account for some non-linearities in your system because these are dynamic linear models that change based on conditions. You don't have to have gigantic, huge, expensive distributed control systems in order to do this type of analysis. There are smaller software packages that can do it for you. You can do it in MATLAB. There's a special tool, system identification toolbox. You can do time domain and frequency domain data, and it can analyze and kind of guess what type of model. You can propose that it might be a fourth order model. I don't know how you would decide that, and I've talked to control PhDs, and they also say, you don't really have a way of knowing whether it's second order or fifth order. You don't know, but you can take a guess and say it's second order and see what MATLAB comes up with and see how well it matches your data. Here are some other companies. This is Control Station. I'm going to be showing you a lot of good graphs and a lot of good information that comes from the founder of this. He's a professor down at University of Connecticut, and I think he's been quite successful with this software Control Station, and he has a lot of insight into how control is really done. And here's another company. I believe this is a South African company here, Techmation. They make some hardware that you can bring on site called ProTuner. We're going to take a look at how that works. It's quite insightful. Here's an example of how ProTuner 32 does its job. Here you see the data. This is real data coming from the output of a plant, and here's your controller output in your open loop test. And look what they do here. You have the time domain data, and how do you find the transfer function? Well, here's the transfer function of the process is just the output of the process over the input of the process in the Laplace domain. And what is the input to the process? It's the controller output in this case. And you have that time domain data. So what do? You just take the Laplace and look, there you are. You're taking the Laplace transform. And now there's another little question about this part, a little mathematical detail, which is quite a serious detail. And how they get data to infinity is, as you can see, it's in steady state here. So you just pad a huge amount of data at the end of this data here. You just pad it with the steady state value to simulate a value going to infinity, so you can do a summation. Of course, now the computer would be doing this with summation, and then you get right there's your result. There's your transfer function. I've seen some examples of the type of polynomials that result from, and they're huge. I mean, it was like a seventh order polynomial, which that's something that would only be done by computer simulation, and according to the Techmation, according to the people who use it, it's pretty accurate in a lot of cases. But there's a problem. Even if you do have a really good model and the computer does do the tuning using, for example, internal model control, and it decides that that's the tuning it's going to implement, computers cannot always decide what is appropriate and inappropriate tuning. Somebody had to program that computer to make that decision, and sometimes it's not always that easy. Auto-tuning tends to have a reputation of not being very good. And here's an example. Let's take a look here. So in this example, here's the PI control, and here's PID control. And this comes from Professor Doug Cooper from Control Station that I was talking about. In the PID control, you can see the PID response is a lot better. You can see that the rise time is the rise time here is less for it to jump up here. You can see it overshoots slightly less, and there's a little less undershoot, and certainly the settling time is better. Overall, the PID response is just better. But now let's look here. Look at all this noise that's coming out in the controller output when you have it in under PID control. If you're putting this type of output into like a valve or into a motor, that's not healthy for the valve or the motor. These real mechanical actuators are not going to respond well to this type of noise. So in this case, the PI control would be better, but a computer might think that this was better. So what does this mean? Well, that's actually good news for us as humans, because it means that INC technicians and engineers are needed to go out into the field and perform tests and do the tuning. So how do you analyze this data? What are these? Now we're going to go into some more detail about these things, dead time and gain and time constant of the process and what they mean. So let's say you do your open loop test out in the field, and you want to know how do you analyze this? What is the time constant? It's the time here. You look here. This is it here. This is the process time constant. It's the time it takes for the process. This is the output of your process variable, or the ultimate thing you're trying to measure. It's the time it takes. Here's the total response of it. It goes from here to here, and here's the amount of that total change. The time constant of the process is the time it takes to drop or change by 63% from this value to this. If 63% of its total change, that's the time constant. And where that number comes from, that's this number is derived from a first-order differential equation that's kind of assumed to represent this process, and we're going to go into more detail about that. Now we're going to talk about the dead time, and here it is here. This time between here and here is the dead time. Now look, the controller. You put your step on the controller, and look here, the process variable that the controller is controlling doesn't respond right away. It takes a while for it to start responding. So this time here, where it's kind of not doing anything, it's not responding very well, that's your dead time. Now that's really up to your judgment. You might say the dead time ended here because you see it going down just slightly. You might say it ended here because you see it going down slightly here. That's really up to you. It's a matter of judgment. And finally, we're going to look at the process gain. What is the process gain? It's the ratio of the controller output, the percentage increase in the controller output, to the percentage change in the process variable, the thing you're ultimately trying to control. Now, basically, it's how much you get out for how much you put in on the controller. It's this ratio here, and you can see here that there's a bump from 38% to 42% of total controller output, so you got a 3% bump there, and you can see that it affects the your process variable. It decreases by 1.6 degrees, so then you get this ratio here, and that's your process gain. Now this is a pretty good example of how you want to use small bumps on your controller output. You don't go from 0 to 100. You're going from 38% of total output to 42% of maximum output. You're not going from 0 to 100. That would be way too damaging to your process. This process happens to be a heat exchanger. Who knows what the precipitous drop would be here in your temperature if you jammed this all the way up from 0 to 100. Who knows what would happen to your equipment if you change the temperature that quickly. So you don't want to do that. So now we can analyze. We've obtained the time constant, the dead time, and the process gain, and we can do some analysis. And yay, we get to start with this nice differential equation. I mean, no, this is an assumed model. We've said that our model is probably going to be this one, and this model happens to fit a lot of chemical processes and a lot of processes you find in heavy industry. So let's start analyzing it. Oh, wait a minute, you've never seen this differential equation before. Frankly, I don't want to look at it. I don't want to deal with it. No problem. You've got these values here, and experience over many years has yielded these empirical formulas based on these measurements, the time constant, the dead time, and the gain of the process. And then from this you can yield your familiar PID parameters here. And you can see these values come from Doug Cooper, the professor from Control Station. But there are many other, these are by far not the only set of empirical formulas. There are so many out there. This happens to be one of them. And you might ask if this really works. The answer is yes. These formulas are empirically verified. They've been used many times, and that's why they're out there. So now we're going to a little bit of how it works. So here's your ideal PID controller. That's your controller here, and it creates the output, the controller output U of t, and what it's operating on is the error that's coming into it between the set point here, your desired set point, and your actual output in your process variable. And it does the proportional, integral, and derivative action on there. And you see here that you've got your friendly proportional gain here. You've got your integral gain, which is formulated as Kc over Ti. You might see this as Ki a lot of places, but this is really what it is. And also Kc Td. You might see this written as Kd, but this is what it is. They all have Kc in them. That's going to be important. We're going to get into that in a bit. But then the question is, what do you do with these formulas? Okay, so you've got your PID controller, and you've seen where these factors are, and you've seen how to obtain them, but okay, what do you actually do to tune your controller? Well, what we're talking about here is real distributed control systems that have equipment like this. This is the Allen Bradley PLC-5 PLC. It's a very famous and well-known PLC. There are a lot of experts out there. There are a lot of forums. You can get a lot of help. A lot of people are willing to share their knowledge about different tricks and techniques, and that's certainly the way control is done. There's a lot of word of mouth and a lot of talk, and you've got to seek knowledge from these people, these technicians who really know how this stuff works. And here's how it's really done. So you did your measurements, you found the gain and the time constant and the dead time, and you found those through your analysis in MS Paint or with a ruler. And then you did your computations on your calculator, and you plugged them in here in this nice Windows 98 GUI. Look at that. There's your proportional gain, your integral time, and your derivative time. There they are. You work them out here, you plug them in here, you press enter, and this Windows 98 program will send it to the Allen Bradley PLC-5, and that will implement your controller. That seems pretty easy to me. Well, you might not be satisfied with that explanation. You might not want to just put values into a GUI and press enter. So let's find out how it really works. So here you've got your standard PID parameters. You've got your proportional gain, your derivative time, and your integral time. And where do these things show up? Well, they show up in the output of the controller. Here's a graph of the output of the controller. This is U of t. Here's U of t, the equation that dictates U of t for the ideal PID controller. You've got your proportional term, your integral term, and your derivative term. And what do you notice about this? Well, one thing you notice is that the proportional gain shows up in all three of these terms. This one often is written just as, this whole thing, Kc over Ti, is often written just as Ki, and this one, Kc Td, is often written as just Kd. But physically, this is what it is. The proportional gain shows up in all of them, and in some physical implementations, you can actually see how the proportional gain is fed into the integral term and the derivative term, and it really is there. So the question is, look at them, they're all here, and if you look here, they're all showing up simultaneously. Not only mathematically are they all interlinked by the proportional gain, but also they're all showing up in the controller output simultaneously. So then how are you supposed to tune your PID controller if you can't see the proportional, integral, and derivative terms independently? You can't change one thing about them and see see clearly what the effect was. Not only are they all interlinked mathematically, but they're all appearing simultaneously. How can you tune it? And another related question is, it's all fine and good to say here, I plugged into these formulas and got these parameters for my PID controller, and I'm going to tune it. Okay, well, what are you actually tuning? Where is your PID controller? How is it implemented? Are you changing resistors on it? What are you doing? Well, the answer is that modern PID controllers are implemented in software. You're going to find this type of code. Here's an example of some real production code from this company, MicroStar. You're going to find this in your PLC on the shop floor. And you'll notice here that the proportional gain, the integral time, and the derivative time, they're just declared as variables. So you can really put whatever values you want in there. And these empirically tuned formulas that you calculated on your calculator after measuring them on the graph, those are pretty good choices. Those are empirically verified. Then the PLC just runs through the code based on the values you've given it, and it performs this calculation. It performs the integral and derivative and proportional math and provides a numerical output, this value u of t, that gets fed into your process. Well, you might not be satisfied with that. You might say, okay, well, I know for sure that they were doing PID control before the advent of the computer, and they were using like pneumatics to do it and hydraulics to do it, so there has to be a way to tune these things. How did they do it back then if they couldn't just plug it into a variable and let the computer do the math? Well, we've actually done this at UBC and EC361. We implemented a PID controller with op-amps. We had 5 op-amps. Here's the proportional, integral, and derivative, and then we had a summer over here. And in this case, you could very well measure the gain between here and here, and here and here, and here and here. You could measure the gains independently, so you could tune them that way, and you tune. But the thing is, if you've ever done that, which we have, you don't really want to do it again. And if you're a company, why would you fiddle around with that? Of course you're going to use something like this. This is so much more powerful, and it's so much easier and more robust. Well, you still might not be satisfied, because you might say, wait a minute, I've learned all these sophisticated techniques. I've learned Q design. I went into the Nyquist domain. I know all about root locus. Can't I apply that when I go work in a refinery? Well, there's nothing wrong with these techniques. And they absolutely could be used if you had a good enough model, and they certainly are used we already mentioned, like integrated circuit design, mechatronics, aeronautics. There's many sophisticated applications where those techniques really are used to tremendous effect. And you might have seen this differential equation that we saw earlier and say, hey, you assumed this was the model of your plant, and there's no reason why this first order differential equation couldn't be taken into the Laplace domain, and then you could do Q design on it or pole placement on it, use all these techniques. And furthermore, you might argue and say, hey, look at these, you got the process time constant, you got the process gain and the process dead time, these things that you measured, and these same factors are showing up here in your empirical formulas. Maybe these formulas here aren't really so empirical. Maybe they're somehow derived from this differential equation. Well, no, that's not the case. Just because these factors show up in both the differential equation and also in the empirical formulas, that doesn't mean that they're somehow derived. The process time constant and the process gain and the process dead time, these are physical features of system responses. We saw an example in that video where the technicians were actually measuring them, and they took the plot into MS Paint and measured out the time delay, and they measured the gain and they measured the dead time. So these things are physical features of reality. It so happens that this model was found to match these measurements and use those type of measurements that are frequently found in system responses. And as a separate effort, many sets of empirical formulas, such as this set here, have been come up with that come up with good factors for your PID control, good parameters. The process time constant and the process gain and the process dead time, these are physical features of system responses. We saw an example in that video where the technicians were actually measuring them, and they took the plot into MS Paint and measured out the time delay, and they measured the gain and they measured the dead time. So these things are physical features of reality. It so happens that this model was found to match these measurements and use those type of measurements that are frequently found in system responses. And as a separate effort, many sets of empirical formulas, such as this set here, have been come up with that come up with good factors for your PID control, good parameters. It so happens that the process time constant, process gain, and process dead time, these things show up really in the time domain data that you get from bump tests all the time, especially in chemical processes and things you're going to find in heavy industry, which means that this first order plus time delay differential equation is in fact a pretty good model of a lot of processes you're going to come across. But as a separate effort, you've got these empirically verified formulas that use these measurements that you took, and they also show up in the differential equation. And you want your differential equation to have those because those factors, because those measurements are the real measurements you're going to be doing, and that's how you can actually start to use your differential equation and find what those factors are. Okay, well, let's try to take this into the Laplace domain and see what happens here. I just took the Laplace transform of this first order plus time delay differential equation, and then let's rearrange it. And here you go. So this might be familiar to you if you've taken EC 460 or some control courses. This is your Laplace domain first order plus time delay model. And there's really no reason why you can't go ahead and do lambda tuning or pole placement or Q design on this. And in fact, we saw before with some modeling software like ProTuner 32, you did indeed get a model of the plant. It did result in a polynomial, and sure, yeah, you can absolutely go ahead and do lambda tuning on it. And in fact, model predictive control and other DCS, they're using model predictive control to do the same type of techniques. They are using them to some extent. In aerospace or in other ultra high performance applications, they want to push the model to its limits. They're pushing the limits of stability to get the most possible performance out of their system, and doing crazy things like making planes with wings that are swept forward, that are unstable all the time and need to be constantly stabilized over and over again with control. That is only done with sophisticated modeling and sophisticated tech. But again, we're talking about like a mine or a refinery, and these gentlemen have been doing this for years, and it's just not used that much, according to them and according to other people that I've spoken to. And it just kind of intuitively makes sense as well. You're not going to be seeing a lot of Nyquist plots in a mine. Bump testing and empirical formulas, on the other hand, you've got many clever technicians out there that are very familiar with how to do this, and they've done excellent tuning, and they've got very efficient and profitable processes in these industries. These processes, one aspect of them is that they have unpredictable behavior, and it's kind of non-linear. Will Wagoner gave the example of valve hysteresis as a common problem, is why you can't just easily model these things, because they behave well in one direction and not in another, or they behave well sometimes and not others. It's not going to be easily modeled. You're not going to easily be able to come up with a description of it. It's not going to be easily modeled. You're not going to easily be able to come up with a description of it. It's not going to be easily modeled. You're not going to easily be able to come up with a description of it. It also happens that tuning methods, even the old tuning methods like Ziegler-Nichols or even trial and error, the technicians that are in the field are clever people, and they get excellent results. They get very low response times. They get very low overshoot. They know how to tune these things just by trial and error or Ziegler-Nichols, and so tuning method ultimately isn't that important in a lot of applications. If you are wanting to use sophisticated techniques, then model identification and getting a good model is going to be the hard part. And that's one of the major areas of research and investment in model predictive control, is the kind of the current rage, and you're going to find that in very expensive distributed control systems. So in summary, distributed control systems are used by big companies in heavy industry to make their processes operate efficiently and profitably. When it goes wrong, safety that we're talking about, control is not only in control of just efficiency, it's also in control of safety, and also we're dealing with could be dangerous processes with high temperatures and so on. Millions of dollars can be lost if these systems go wrong, and certainly if safety critical systems go wrong, you could have environmental damage and death. Distributed control systems are composed of local actuators, motors, valves, pumps, the sensors that sense the level of the processes you're trying to control, and then you've got the local logic and the programmable logic controllers that are mounted near your process. You've got the input-output units that are receiving analog and digital signals, and then you've got the high-level monitoring and the high-level model interpretation software. Modern technology like wireless is making it easier. The wiring becomes less of a problem, and of course the equipment gets better all the time as these companies compete to get more of the market share. Control is usually performed locally. It's not in one central location, in one central control brain. It's in PLCs that are all over your plant. There are thousands of these controllers all over your plant. and they all need to be tuned to keep the plant running as efficiently as possible. For the most part, you've got technicians out there doing bump testing and tuning in these heavy industries. The distributed control system algorithms can try to auto build and do auto tuning, and to some extent it can do that, but it's not considered to be trustworthy. And Laplace domain techniques are not really used in these, as far as I've seen, they are not really used in heavy industry that often. System identification, model identification is a big issue. When you want to use those techniques, you need to have a good model. The best models you're going to be getting are with data from open and closed loop testing that's been done for many years now, and is that's a science in and of itself. The data is used along with well-tested empirical formulas, which can be used by technicians, or it can also be used even by more sophisticated Laplace domain techniques, and then you can tune your PID or other controllers with it. Technicians will mostly just be entering that data into the programmable logic controller, or they'll be programming their own logic, which can be very sophisticated. It's not to be underestimated, and that's how tuning is implemented. And that's my presentation. I hope you are satisfied about learning about real control in heavy industry.